Okay, I want to show you a kind of neat application of Green's theorem. So I have what here on the board, what I would refer to as a blobular region. It looks like a blob. And it has a boundary curve, C, which is oriented counterclockwise. Now I know that the area of D is just the double integral over D of 1 dA. And for lots of regions, that's a very convenient way of finding the area. But for some regions, the limits of integration just get messy. Either they're difficult to find, or they're kind of a pain when it comes to working out the integral. So what I'm going to try to do is I'm going to hope that this integrand right here actually matches the formula for what I would integrate if I were using Green's theorem. So if I have a vector field F, and it's P of xy, Q of xy, I know that what I integrate using Green's theorem is the determinant of this 2 by 2 matrix. That would be the partial of Q with respect to x minus the partial of P with respect to y. So I'm going to hope that I can find some vector field so that the difference between these partial derivatives is just 1. If I can find a vector field that satisfies that, then I could actually find the area by doing the work integral of that vector field around the boundary curve C. And it turns out there are actually 3 very easy vector fields that I can get. So I'm going to first of all create what I call F1. Now here I'm going to use the brilliant observation that 1 is equal to 1 minus 0. So I want the partial of Q with respect to x to be 1, and I want the partial of P with respect to y to be 0. Now there are infinitely many choices because these are just partial derivatives and antiderivatives aren't unique anyway, but I'm going to pick the simplest thing I can. So the simplest function I can think of, whose partial derivative with respect to x is 1, would be x. And the simplest function I can think of, whose partial derivative with respect to y is 0, would be 0. If I have this as my p and my q, the partial derivative here with respect to x is 1, the partial derivative with respect to y is 0, I'm going to get 1 minus 0. Nice. All right. I can also find F2. For F2, I'm going to use the brilliant observation that 0 minus negative 1 is equal to 0. So I'm going to want the partial of Q with respect to x to be 0. I'm going to let Q be 0. That way its partial with respect to anything is 0. That means I want the partial of P with respect to y to be negative 1. Let's let P be negative y. Those are the simplest functions I can think of that are going to work. And all I'm doing is taking advantage of some very basic arithmetic. 1 equals 1 minus 0, and 0 equals 0 minus oh my goodness, I didn't even write that correctly. 1 equals 0 minus negative 1. That would be a true mathematical statement. Okay, there's also a third common choice if you want to do this, and that's just to take the average of these two. So take negative y over 2 and x over 2. That way when I take the partial of this with respect to x, I get a half. When I take the partial of this with respect to y, I get negative 1/2. And now I'm using the brilliant observation that 1/2 minus negative 1/2 is also just a way of building 1. Okay. So that gives me 3 common choices. Obviously, this is not an exhaustive list because there are lots of different ways that I can build 1. But it turns out I can just do a line integral instead of doing a double integral to find area. Now, one place where that could be useful is if I wanted to work with an ellipse. So let's say I want to find the area enclosed by x squared over 4 plus y squared over 9 equals 1. So that's a beautiful ellipse in the xy plane. We're coming out 2 in the x direction, 3 in the y direction. That's my beautiful curve right here. Now, if I'm applying Green's theorem, I'm going to want to make sure that that's oriented counterclockwise. And I'm going to find the area by doing a line integral around this curve. And I could actually work with any of these line integrals. Let's just go with this one. Let's use f1. Okay. Why I might want to do this is just that the limits of integration for an ellipse end up being kind of messy. Okay. So if I were going to find the area here, I think I have two good options that I like. One would be to choose a change of variables, so to take a disk and morph it into this ellipse, and then use the Jacobian and switch to integrating over the disk. The other would be to use Green's theorem and integrate around the boundary, because the boundary is actually easy to parameterize. I could simply say r of t is going to be 2 cosine t, 3 sine t, as t varies from 0 to 2 pi. Okay. So I'm viewing this as just a morphed circle. I've stretched x by a factor of 2. I've stretched y by a factor of 3 to make sure that it's counterclockwise. I've got the cosines in the x position. Okay, excellent. So then r prime of t would be negative 2 sine t, 3 cosine t. And so if I wanted to integrate around c, f1 dotted with t ds, I know that would be the integral from 0 to 2 pi of, I'm going to take my vector field, which was 0x, and x was 2 cosine t. I'm going to dot that with r prime of t, which was negative 2 sine t, 3 cosine t dt. This is going to become the integral from 0 to 2 pi of nothing plus 6 cosine squared t. But now I can use my double angle formula. So I can say this is the integral from 0 to 2 pi of 6 times 1 plus cosine 2t over 2 dt. I can cancel that 2, and I'm going to factor out that 3. So I've got 3 integral from 0 to 2 pi of 1 plus cosine 2t dt. And we'll do our quick u sub. U is 2t, du is 2 dt. I want a 2, so I'll counterbalance with a 1/2 on the outside. All right, so 3/2 integral from 0 to 4 pi now, and it's 1 plus cosine u du. So that's going to be 3/2 u plus sine u, evaluated between 4 pi and 0. That's going to be 3/2. When I plug in 4 pi, I get 4 pi plus 0. And when I plug in 0, both terms there go to 0. So I'm just getting 6 pi. So kind of neat. Might be simpler than using the Jacobian and a change of variables. Now, I will not on the exam require you to find an area using Green's theorem. So it's a neat trick. It's possible that I will ask you to find an area and not specify what technique to use. You are certainly allowed to use this technique, but I will not require you to do it. So I don't want you to feel like, oh man, I got to memorize all these functions. They're not that difficult, because it's just 1 is 1 minus 0, or 0 minus negative 1, or average the two vector fields that you get from those two cases. So it's not super complicated, but it's kind of a neat trick. I'd rather you focus on really having the fundamentals down. So you're allowed to use this technique for finding area on the exam, but I will not require that you do so. And if I ask you to find an area, there will be another technique that we've covered this semester that would work for that area. So you can add this to your bag of tricks, but don't spend a lot of time focusing on, I must know how to find the area by Green's theorem, because I won't require that you do that. I might require that you do an integral using Green's theorem, but it wouldn't be to find an area.